Welcome back to my channel. I will continue today with the notion of the transfer function for single input, single output systems. LTI systems, linear time invariant systems, are usually described by a set of differential equations. Here we are limiting ourselves to single input, single output, linear time invariant systems. So those systems are described generally by a set of differential equations. Here we have one example of a SISO system described by only one differential equation of that form. So the notation y between brackets n, it means differentiation of y, differentiation of order n of y dtn. Okay, same thing applies for the rest. Okay, in order to get the transfer function, we will compose the Laplace transform to both sides of this differential equation. So we will start with this term. We know that y, the nth derivative of y with respect to time, its Laplace transform is snys. snys. The Laplace of this term is bn minus 1 s power n minus 1 times ys. And we will continue until we arrive to this term. We will have b1s ys, and here we will have b0 ys. So here we will, when we apply the Laplace transform, we will get s power m us, and here we will have m minus 1 s power m minus 1 us. We will do the rest until we arrive to a0 times us. So we can make here ys in factor, and we can make here, okay, u in factor, okay? And then we compose ys divided by us. We will get the transfer function gs defined as numerator ns divided by the denominator ds. Pay attention when you compose this transfer function. You should put it as a polynomial over a polynomial. Because if you are expressing this gs in terms of rational terms here or here, okay, you cannot distinguish the notion of poles of zeros that we will define now. So you have to put your transfer function as a polynomial over a polynomial. So the order of your system, it is the highest order of the denominator. Okay, generally m is less than n in case of causal systems. Okay, we may have m equal to n as a limit, okay, of realizable systems. Okay, but when the order m is greater than n, generally the system is not realizable in the notion that we have seen in our previous lectures. So now the order of the system, it is the order of the polynomial of your transfer function. Okay, so in this case we can say that the system is of nth order. What are the poles? The poles are the roots of ds. It means the roots of the denominator of your transfer function. What are the zeros? The zeros are the poles of ns. It means the numerator of your transfer function. So the roots of ns will be called the zeros of the transfer function, and the zeros of ds will be called the poles of your system. We have identified the class of BIBO systems. It means bounded input, bounded output systems, to be the class of stable systems. Okay, and this characterization was in the time domain. Okay, so the input was a function of time, the output was a function of time, and if the input is bounded results on an output which is bounded, we can say the system is bipolar. How can we characterize this notion in the frequency domain? So you see here that we are in the S domain, or the complex plane, where here we have the imaginary axis and here we have the real axis. So the left-hand side of the complex plane, the whole left-hand side of the complex plane, is called the stability region. It means the area where the system can be stable. So here, if the poles of the systems are located here in this region, it means when the real part is negative, the system is said to be stable. Here I will show some examples of operational amplifiers circuit where we are asking to get the transfer function of these circuits. It means the relation between the input and the output, or output over input, is called by definition the transfer function of the operational amplifier circuit. So here we have two basic components, a resistance and a capacitor. And first of all, we will replace the capacitor by its impedance. And we know that the impedance of a capacitor is 1 over j omega c. So j omega will be replaced by s, this s, okay? It means the impedance of a capacitor, it is 1 over cs. We can easily verify, because here we have almost voltage equal to 0 between these two terminals. We can verify easily that the ratio V2 minus V1, it is equal to the impedance of the output over the impedance of the input. Impedance of the output multiplied by a sign minus. So we will have 1 over Cs divided by R, which gives 1 over RCS, multiplied by a sign minus. In this example, we have reversed. We put the capacitor at the input side and we put the resistance at the output, right? So now impedance of the output divided by the impedance of the input multiplied by -1 will give minus RCS. And it is clear here, it is a differentiation system, or a differentiator, okay, multiplied by a coefficient RC multiplied by -1. So we can choose RC such that the product RC equal to 1. So this circuit will describe at the end what a differentiator, okay, with inverting, okay, action, which is minus, okay. In this example, we are putting a composite circuit at the entry side, and we have R2 in the output. So the impedance of the output, it is R2, and the impedance of the input, it is R1 parallel the impedance of C, which is 1 over CS. Okay, so R2 divided by the equivalent impedance gives this one multiplied by sign minus. Here we have the impedance at the output to be the sum of R2 plus 1 over C2S. So this is the impedance of the output. And the impedance of the input, it is R1 parallel 1 over C1S. Impedance of the output divided by impedance of the input multiplied by minus will give this result. Here I am showing you how to calculate and form the polynomial starting from its coefficients. You see here that this polynomial P, okay, is of degree 3. Okay, so how many coefficients I will have here? Okay, I will have 4 coefficients. So the first one will be the coefficient of s cubed. 3 is the coefficient of s2. Since I don't have s here, it means the coefficient of s is 0. And the last term, I have 4. It means s power 0 has a coefficient 4. By writing p as a vector, as a simple vector, and then follow it by the instruction roots, so MATLAB will understand that the p is asking for the root of a polynomial written in terms of its coefficients, and here it will give the roots of this ps. It means ps equal to 0. If ps is describing a denominator of a transfer function, we can say that this system is not stable because we have 3 roots, one of them is negative, and the 2 remaining ones have a positive real parts. So these 2 poles, okay, if you wish, have a positive real part. Since they are not in the left-hand side of the complex plane, it means this system will not be stable. In the first part, we are constructing a polynomial from its coefficients, and here we are constructing a polynomial from its roots. For example, if we start from here, if we defined r like this, and I would like to know what is the polynomial whose roots are given by this. So I will apply poly as comment. It means give me the polynomial whose roots are given by r. And here you see that we have the same coefficients that we wrote in the beginning. So it means MATLAB is able to identify the polynomial from its roots. Okay, so we have 2 options. We can define a polynomial from its coefficients, or we can define a polynomial from its roots. We can multiply or make a convolution of two polynomials in S. For example, if I would like to multiply 2 polynomials, so I will construct them first as vectors, and then I will follow these instructions by conv of pq, where pq are polynomial in S. So if you multiply and simplify, if you expand this, you will get ns equal to this, okay, which is the product of these times this. I can also evaluate a polynomial at a point by using the instruction polyval. It means evaluation of a polynomial at a point, at some point s, okay? So here I will evaluate ns at s equal to -5, and this comment gives minus 66. So here I am creating 2 transfer functions, S1, Sys1, and Sys2, using numerator and the denominator. It means the coefficients of the polynomial of the numerator and the denominator. I can then construct system 1 by the instruction TF, numerator, denominator. So I will get this transfer function. I will do the same for this. So I have 2 different transfer functions. And then I can sum them by using plus, a simple plus. So if you put Sys1 plus Sys2, it's like you are adding these and these together, okay, which gives this one. You can evaluate the poles and the zeros of the transfer function by using the instructions poles and zeros, okay. So if you define the system as with a transfer function by this instruction, it will give you this transfer function, and then you use pole. So the pole of Sys will give you the poles. It means the roots of this polynomial, which is -1, -1. The zeros of your system will be the roots of s plus 10, which gives z equal to -10. The instruction pzmap of a Sys where the sys is defined as a transfer function, will give you the location of the poles and the zeros in the complex plane. So these instructions help you to see where the poles and the zeros are distributed in the complex plane. If you have two systems in series like this, okay, I can evaluate the equivalent system here, which will be the product, because we know that an output here will be the product of U times G1. And an output Y here, it is this input, which is here, times G2. It means I will have G1 times G2 times U. And at the end, the Y will be G1 times G2 times U. So this can be done by the instructions series sys1 times sys1 sys2. Okay, so we don't have G1 times G2, so we will write series sys1 sys2, where sys1 sys2 are defined as transfer functions. So this is an example of two transfer functions connected in series. If we apply the instruction series of this system, system H and system G, okay, we will get the product of the transfer function as shown here. Now, the output of system which is written in blocks like this, blocks that are in parallel. So the output here, it is U times G1. And here the output here is G2 times U. So the Y will be G1 plus G2 times U. So this system is seen as a set of blocks that are composed in parallel. So if we will apply parallel sys1 sys2, is like we are adding G1 plus G2. Okay, so we have here an option to put sys1 plus sys2 or parallel sys1 plus sys2. This system is known in the literature to be a system in feedback form, because we are feeding, okay, the system, the input, by something related to the output. Okay, so here generally we have some transfer function that is characterizing the control action, and here we have our basic process or system, which is given by GS. Now, these two systems, these two subsystems, we can replace them by one block, which is GC times G. Okay, and here we have a unity feedback. It means it's like I have what? I have a block here, and I have one, coefficient 1. Okay, so we call it unity feedback because we don't have any block here. So we are just feeding the system from the output. We have a special instruction or command in MATLAB which give us the overall transfer function y divided by r. So y divided by r will be given by feedback system 1. It means this block, okay, which is the product GCG. And here I have unity feedback 1. I put 1, and here sign. If I will put plus 1, if I put here plus, it means here I will put plus. If I will put here minus, it means here will be minus. If I will omit the sign, this third argument, it will taken as minus. It means negative feedback. So y divided by r, you can easily prove it that it is g divided by 1 plus gh when you have negative feedback. And it is equal to g divided by 1 minus gh when you have here a positive feedback. So if you define now the transfer function gs and hs alone, okay, by the instruction tf, and then you compose the instruction feedback sys1 sys2, and you put a sign to define this sign, if it is positive or negative. It means that you have to put here plus 1 or minus 1. Or if it is always -1, you don't need to put the third argument. Okay, so this will give you the overall transfer function, which is this or this, depending on the sign of the feedback. So this is just a direct application of the feedback comment of MATLAB. So in the first line here, we are defining this GS, and here we are defining the transfer HS. And at the third step, we are composing the transfer function YS divided by RS, which is given by the instruction feedback. So this gives the results which is shown here. Sometimes we may have poles and zeros that are equal. If they are equal, we may reduce the order of the transfer function by simplifying the zeros with the poles. And this is why we have here in MATLAB a command which is minimal realization of systems that can simplify for us the transfer function if we have zeros poles cancellation possibility. So in this example, the denominator of the original system, okay, is of order 6. Okay, now here we have some zeros that are equal to some poles, and one pole is equal to some zero. Okay, in this case, you see that when we apply the minimal realization instruction, we have reduced the order of the transfer function by 1. And the final or the simplified transfer function in this case is a 5th order transfer function. The notion of the transfer function help us in composing complex systems that are composed by electrical and mechanical components. For example, for the DC motor, its internal structure is composed from an electrical part and a mechanical part. Okay? And we have a link between the mechanical and the electrical part. For example, if I will focus on this primary circuit, we can compose the voltage, the Kirchhoff voltage law, to get the relationship between the voltage VF and the current IF flowing here. Okay, and this is described by a transfer function of order 1, and you all see it here. The relationship between the voltage VF and the current IF, where VF of S and IF of S are the Laplace transform of VF of t and IF of t. So here I am composing this part, and then the electrical part is connected, or it is related to the mechanical part through a coefficient. It means the torque of the motor, it is proportional to what? To the current in the primary circuit. Okay, so here we see the torque of the motor is Km multiplied by the current IF. If I don't have any disturbance, this torque motor is equal to what? So here I am describing the dynamics of the rotor, and I am applying the second law of Newton, okay, to get the dynamics in time. What I will write? I will write J, the inertia, times theta d dot will be equal to the sum of the torques applied to my system. Okay, so here I assume that I have a friction. So I will have J theta d dot will be equal to minus B, okay, minus B theta dot, okay, And this part that you are seeing here, it is exactly the Laplace transform of the differential equation describing the dynamics of the rotor. Okay, and you see the electrical, mechanical, and I can also add some eventual disturbance that may act on the rotor. For example, if I will put here my hand to prevent the motor to spin, okay, in this case, I am seeing my finger, the torque that I am applying here, okay, as a disturbance, okay. So we may have a disturbance and we may not have a disturbance, okay. It's like, for example, you have a motor, you have an electrical car, and this car is what? It is facing a stone on its road, okay. So this stone is acting as what? As a disturbance, okay, as a disturbance to what? To the motor. And here, this action will be included in the model of the overall system.